Once again, recall that if we know the answer to a derivative problem, then we can reverse the process and find the answer to an integration problem. So since we know that the derivative of a to the x, where a is some base other than e, requires us to have that factor of natural log of a in the answer, we can do the same thing in reverse when we integrate. The antiderivative of a to the x dx is simply going to have a factor of the reciprocal of the natural log of a. And that should make a whole lot of sense if you check your answer with differentiation. Because when you take the derivative of a to the x, you're going to get that natural log of a that's going to need to cancel out with the 1 over natural log of a in order for our coefficient to be 1. So that's really all there is to it. Everything else is the same old strategies that we've dealt with in the past with integration. So for example, since this is not an x but something more complicated than x, then we're going to let u equal that x value, right? U equals 3x, so du over 3 equals dx. So that means that we have a new integral that's going to be 4 raised to the u times du over 3, or 1/3 times 1 over the natural log of 4 times 4 raised to the u plus c, which can simplify down to 1 over 3 times the natural log of 4 times 4 raised to the 3x plus c. Right? So it's the same process, except we have this extra factor of natural log of 4 in the denominator, and that's literally the only difference here. Some people will go a little crazy with their properties of logs and start condensing things. You're welcome to. I don't see any need to do that. Leave it as 3 times the natural log of 4, and that's perfectly fine. Same strategy here. We're going to let u equal that exponent of x squared. So du over 2x equals dx. And this is a pretty standard u substitution problem. We're going to get x times 5 raised to the u times du over 2x. And that's when we see, oh yeah, the thing that needs to cancel out here, the x, does cancel out because there's 1 on the numerator and the denominator. So we have a 1/2 left over. We've got 5 to the u du. And if we're doing this right, then 5 to the u, or any number to the u, is going to be our only integrand, and then we're just going to use this pattern up here, this formula. So 1 over 2 times 1 over the natural log of 5 times 5 to the u plus c, and when we sub back, we get 2 natural log of 5 times 5 raised to the x squared plus c, and that would be it. All right. These next two problems work pretty much exactly the same way. Actually, I take it back. This first of this next two problems does not work the same way. We're not going to let u equal 3x. Because if we do, we're going to get a 2 to the u over 5 plus 2 to the u, and then we're still kind of stuck. So then we might need to do v substitution and let v equal something else, and that's fine. Or we can just do it all in one fell swoop here and let the denominator equal u. So if we let u equal 5 plus 2 raised to the 3x, then du, I'll do this the long way, equals the natural log of 2, that looks like a subscript now, natural log of 2 times 2 raised to the 3x times, don't forget the chain rule, times 3. So that means the du over 3 natural log of 2 times 2 raised to the 3x equals dx. And that 2 raised to the 3x in the denominator is good news because we've got a 2 raised to the 3x in the numerator. So we'll go ahead and rewrite this as the integral of 2 raised to the 3x over, well, this whole denominator is u, so over u. And then instead of dx, we'll do du over 3 natural log of 2 times 2 raised to the 3x. And as I just mentioned, that's great because 2 raised to the 3x divided by 2 raised to the 3x is gone. So we've got a factor here in the denominator that we can factor out. And then we've got an integral that we haven't seen today, but we have seen many, many times in the past. We know how to integrate this with our eyes closed and both hands tied behind our back, right? Natural log of the absolute value of u is all it is. So we've got 1 over 3 natural log of 2 times the natural log of the absolute value of 5 plus 2 raised to the 3x plus c. And that's it. I would mention that some people like to leave off the absolute value bars when appropriate. For example, 5 plus 2 raised to the 3x is always positive. So we don't need the absolute value bars here. I'm going to leave them in there because why bother messing things up? So it's safer to just leave them there. All right, great. So moving on to this last problem on this page, we have, this one's going to look a lot more like the other ones where we're just going to set the u value equal to the exponent. So let u equal the cosine of x over 5. So don't think about the quotient rule here. That's certainly not necessary when the denominator is just a constant. Cosine differentiates to negative sine. And then the derivative of x over 5 is just 1 over 5. So when we solve for dx, we got a 5 in the numerator, negative 5 in the numerator. We'll put a sine of x over 5 in the denominator. And that's perfect because the sine of x to the 5th is going to cancel out. I'll go ahead and write it out anyway. Sine of, not x to the 5th, x over 5, x fifths. So times 5 to the u times dx, which is negative 5 du, over sine of x over 5. And of course, as we've mentioned, the x to the 5th, so the sine of x over 5, rather, cancels out. So we've got this constant of negative 5 that we can factor out, and we've got 5 to the u du. And integrating this should be not so bad. We get the natural log of 5 in the denominator, and then we've got 5 to the u plus c. So this is final answer going to be negative 5 over natural log 5 times 5 raised to the cosine of x over 5. Lots of 5s in this one, plus c.